Thank you, everyone. Are you guys able to hear me?
Indeed, yes, we can.
Okay. Sorry, I have to take this call from my car because right after this meeting, I have an industry visit. Thank you, everyone, for all the interesting presentation and the work. And the project I will be describing has a lot of similarity with the one that Nick is doing. So, um, what we are doing at Red Deer Polytechnic, we are using our campus as a living laboratory to test different technologies from the industry, as well as we are building our own technology to make our campus more energy efficient so that we can run efficiently within our campus. Next slide, please. So what you see in this picture um, is a bird's eye view of our campus. And so on the very right is the highway, Calgary Trail. So some of you traveling from Edmonton to Calgary or live around central Alberta is very familiar with this particular building, which has a carved roof. It's our game center. Then as we move towards the east, we have our main campus. So the main campus consists of libraries, there are classrooms, there is a big trades department which have a lot of welders, a lot of machineries running, and then we have our innovation centers, which also have a lot of equipments running. So one of the innovation center is our alternate energy lab. It's a 5.5 5,000 square meter lab that we have, and so that particular building we targeted to do a pilot scale project, and I'll describe in a bit what the project is. So in that particular building, the HVAC runs almost 24/7, and so there is an opportunity to move that HVAC system from a fixed um, demand to a demand-based control system. So that's what this project is about. And what is the best way of doing that in a system which is old, as well as we can retrofit certain things. So the whole idea is if we can succeed on this pilot, then as I described, our Red Deer Polytechnic is a very multi-use situation. So some of the buildings are occupied from time to time, and the occupancy is very random. For example, the game center, there are games, so it gets really filled up, and then most of the time there are not as much people compared to the capacity of this building. Same with our classroom, same with our innovation center. And it's very unpredictable when there will be a huge demand, where there will be a lot of people in the building, and when the building will go empty. So the idea is very simple. When the buildings are empty or there is not much happening within the building, then can we turn down the HVAC system, still maintain the quality of the air required by ASHRAE, and uh, then make the building more energy efficient. So that's kind of the idea behind this project. Next slide, please. So we have been fostering in Red Deer Polytechnic Internet of Things and data-driven innovation for a while. So our applied research department backbone is data-driven innovation, and we use data-driven innovation in multiple areas, um, for data acquisition and monitoring, then for predictive maintenance of all our asset. This could include all the HVAC system that we have, all the robotics, all the CNC machines which are running, welders. Then we also create digital twins and simulation of some of these assets, especially on the energy side, how the energy demand and consumption, how that balances with the grid. So our campus acts like a living laboratory in its true sense, and it acts like a mini city where we have the flexibility of trying different systems, how system integrate with each other for microgrids. So there is a huge opportunity for industries to partner with us to do this kind of research. And one final piece of the IIoT and data-driven innovation is smart energy management solution. So we are trying to foster this within our campus so that we can um, give this knowledge back to the community, to companies like Nix, like this is what we are doing, and we tested that in a real environment, and these are the results. So that's one of the goal of the project, to give that knowledge back to the industry, to the community. So next slide, please. So as I was talking about our living lab, so we help piloting industrial solution, and then we help SMEs to develop their own technology, plug it into our living lab, and use us as a test bed to de-risk the technology adoption. Next slide, please. So now I'll talk about this particular project, and thanks for SRIA for funding this project and helping us complete this pilot. So this is a problem, and this needs to be addressed in many institutional building, many healthcare facilities. So here are some numbers on the slide of the energy intensity of typical buildings that is in Canada. So it has a range. Some of the efficient buildings are close to 1 gigajoule per square meter, and some of them could be as high as 3 gigajoules per square meter. And the primary reason why this is so high is because these buildings were designed at a time when there was not much attention was given to this particular problem. So they were designed for maximum occupancy, and it was assumed that the building will be always occupied. And then the HVAC was designed based on that, but it is operational also based on that. So in a climate like Alberta's, where heating and cooling is very much required due to the seasonal change in temperature and the temperature swing, it really adds up to the cost. So reducing the energy demand of the building by optimizing HVAC is a good way. Some people do it by using a timer, like my building is occupied from 10 to 5 most of the time. So we'll have a timer where the HVAC runs at a certain capacity, and then some building, um, yeah, but it does not work for most of the building because there could be seasonal occupancy like institutional building, healthcare facilities. So there you have to have a monitoring system that is monitoring your building, very similar to what Nick was talking, and that monitoring system collects intelligent information about your building and then tells the HVAC system through a control algorithm what to do. So I'll move on to the next slide. So in our building, our approach is to put air quality sensor, occupancy sensor, which is people counter, gas meter, and energy metering. So we are metering this particular pilot building, and we are measuring the baseline where the building is sitting right now. And then we have all these distributed sensors around the building, which is monitoring the air quality. So based on the data that we are obtaining, we are making decision based on some AI algorithms in the BMS, which is the building management system, how to operate the HVAC. And I'm glad to hear Nix is even predicting the future um, based on the weather. So that's will be a great tool. So what we are doing, we are collecting CO2, VOC, humidity, particulate matter from the outdoor, and we are making a decision based on how we operate the HVAC. So some of the decisions that the HVAC will be making, keeping the temperature and humidity set point at a comfortable level, is should I bring in fresh air? Should I recirculate the air? And how many times the air get circulated? So these are some of the decisions that the HVAC will be making, and will change the ACH and the fresh air intake based on the requirement within the building. So we right now have developed an AI-based algorithm which is getting training data set from the real operation of the building, and with the SSRIS funding, we intend to retrofit our HVAC system with VFD, and we want to have an open source BMS to try different algorithms. So we'll be trying our algorithm, and we are partnered up with an industry, so we'll be happy to try their algorithm in our open source BMS and then benchmark different algorithms. So that's kind of where the project direction is. We'll move to the next slide. And one important fun fact is, if someone reduces the speed of the fan in the HVAC, for example, if you make your ventilation half, so your fan is now operating at a fan's speed half of what it is, then you save way more power when it comes to the electricity usage, because based on the fan curves, it's proportional to the cube of the fan speed and energy. They have a cubic relationship, so you end up saving way more energy. So when we calculate these, we have a very good energy savings from this building. And if we do it in the right way and everything is optimized, we have a theoretical value of around 87% of the energy of that building we can save. So that's a huge savings for us in operating that building. Not only we save energy today, since the fan and all components will be not running at 100% all the time, so you save life of the equipment as well. So it's a multifaceted benefit. Once this project is the pilot is done, we do want to implement it across our campus, which will have a very good potential for saving our cost and help us become more sustainable and efficient. Having said that, Red Deer Polytechnic has a goal to be one of the first institute to become net zero by 2031. So this project definitely helps us attaining that net zero goal by 2031. We do foster sustainable practices at Red Deer Polytechnic. I'd like to end with that. We have one of the highest rooftop solar panel arrays among all campuses in Canada. So we have 42,000 solar panels capable of producing 1.6 megawatt of power. And as of today, we have the capacity of producing 60% of our energy demand from renewable sources.